My name is Chris Armstrong. We coming in today from RIGOL Technologies. So you've got a couple of our scopes and other DMMs and instruments on the bench there. And really what we just wanted to do was it was nice of your professor to kind of invite us in. But what we wanted to do was take a little time and kind of show you around the meters, scopes, and DMMs so you can see kind of some of the basic features of them and then some of the advanced features. So the goal really today is just to get you a little more comfortable with some of the instrumentation. And hopefully next time you're making a measurement in class, it's easier and more straightforward for you. So what we're going to talk about overall today is signal and instrument basics. So we're going to start with some Ohm's Law, some DC measurements, some pretty basic stuff, make sure we understand that. And in that context, in the concept of DC measurements, we're going to talk about the multimeter and how a multimeter works, what it does in different modes, how it makes those measurements. And then we're going to start introducing some AC concepts, like peak-to-peak versus RMS measurements. What does that mean? What's the difference? Why do we have it? And then as well as some other oscilloscope basics, different things in the oscilloscope, triggering, memory depth, how a digital oscilloscope really works today. And then we're going to talk about some tricks and tips, really sources of error. We'll talk about how bandwidth and sampling can cause errors in your measurements, how you can miss things with waveform capture rates, and how coupling and compensation, loading, affect other measurements as well. And then if things go well, we're going to talk about some signal harmonics. I think one of the interesting and cool things that we can really investigate with this kind of instrumentation is, when you have a waveform that includes multiple harmonics, you start to look at things like square waves, ramp waves, sawtooth waves. How are those really constructed from both a time domain and a frequency domain perspective? And I think that will give you a little insight, hopefully, into how the modern world works, how RF starts to play a role in these kind of signals and systems, and how other types of interference and problems can arise as well. We talk about Ohm's Law as voltage equals current times resistance. And right now we're going to talk about it in sort of a DC sense. All right, so we talk about, again, just from a diagram standpoint, a simple DC source. This is a symbol for an ammeter or current measurement, and we have our resistor in there. So we have a kind of a simple setup here as well. So we've got a power supply set supplying 1 volt. We have that in series with the ammeter. Right? So the ammeter we'll talk about in a minute, but the ammeter presents as a short circuit. Right? So there's no voltage really develops across the ammeter, especially the theoretical model of one. Right? So and then we have a current flowing through this resistor, and so we can make a calculation there. What we do here, so here we've got 1 volt DC, and we've got 10 milliamps flowing. Right? So we know by looking at this and the diagram, we can tell that the resistance, it's 1 volt divided by 10 milliamps, or 100 ohms. Right? From this, we can also, as we move towards AC measurements as well, power becomes real important. Everything these days is about power. How much your battery can supply, the best way to do that, where your losses are, all of these sort of items, right? And so power we often talk about in a DC sense as being V squared over R. You can also talk about it in a true D sense as current times the voltage, right? So a watt is a volt times an amp. So that's a basic DC setup. Let's see if we can't make it a little more clear. All right, so there's 2 ways we can use the voltmeter to measure this circuit, right? When you use it as a voltmeter, we put it in parallel with what we're trying to measure, right? And it has a high impedance connection. What that means is that normal current flowing through the circuit, it won't flow through the voltmeter, right? Because this is much higher impedance, or has an internal resistance that's higher than the device, right? So, here we have sort of the high voltage point, right? And all the current wants to do is get to ground, right? And the best way to do that is through the device, and then through the ammeter. So we'll talk about loading effects later and how, if that ceases to be true, right? If your device becomes very high impedance, or your voltmeter starts to break down, then you have you have in essence a parallel path here, right? And the current starts to flow in two directions. Your ammeter doesn't see all the current anymore, and your voltmeter is affecting the circuit. So, and this is one of the kind of differences we'll talk about between a multimeter and an oscilloscope. Right? A multimeter, like the one on your bench here that we're using, typically has tens of gigohms of input impedance. Right? A gigohm being 1,000 megohms or a billion ohms. Right? So that high impedance forces all the current to flow in another direction. Now, an oscilloscope, the sort of standard passive probes, would still be called high impedance probes on an oscilloscope, but they might have an impedance typically of about a megohm. Right? That allows you to make some different measurements with them. But in a circuit like this, it could also cause loading, right? Because it's only a megohm, and if we had a megohm here, the current would flow evenly. So here we said we have about 100 ohms, so we're probably still okay if we did that. The other way we can use the ammeter, which is another way it's different than an oscilloscope, is we can use it as an ammeter to make this measurement over here. And as an ammeter, the DMM presents a short circuit. Right? So here the special circuitry inside allows the current to flow through uninterrupted, as if there's no voltage developed here. But we're able to measure that voltage. We're able to measure the current that's flowing through directly. So we don't interrupt the circuit, and we can measure both volts and amps directly with a multimeter. Because of this capability, the third way we can use a DMM to make measurements relevant here is as an ohm meter directly. Right? So we can take the power supply out. We can switch it over to ohms and just measure directly across the resistor, and it tells us that this is 100 ohms. Right? And so typically when a DMM multimeter makes resistance measurements, it does that by sourcing a small current and then measuring the voltage. Right? So it does both things. It knows how much current it's sourcing internally, so it's able to make the resistance measurement, the calculation we just did, by itself. And that's why there's another interesting way to do that is the capability, the 4-wire resistance capability, which is why you have the 2 sets of plugs in the front of the DMM. You can separate the wires for sourcing the current and measuring the voltage. And what that allows you to do is really isolate the resistance, right? Because even in this configuration here, we're taking a measurement of the resistor, but we're also seeing the resistance of the wires, right? Because it's just pushing current out these 2 plugs and it's looking for the voltage developed across them. So if this were a sort of opposite to the loading problem, if this were a small resistor, like 1 ohm, right, then we might see 1/10 of an ohm from this wire and 1/10 of an ohm from this wire being added to that measurement. So what 4-wire does is it separates those 2 sets of wires so that the current is flowing in one loop and the voltage is being developed on the other side, but there's no current flowing through the leads. So you don't get additional resistance value added from there. The other thing that, the last measurement that's sort of unique to multimeters, DMMs, is temperature. So temperature is actually measured really in the same way. When you measure temperature with a multimeter, what you're really doing is you're measuring the voltage across a thermocouple, or possibly a RTD or a resistive device. But a thermocouple is the most common way. And a thermocouple is a special connection of 2 different types of metal. And what we have is we have scientific tables that tell us, this connection of 2 different types of metal at this temperature creates a voltage in the junction. And so we can measure that voltage and in essence do a lookup on the table to see what temperature that is. So that's why if you're ever doing temperature measurements in this lab, you'll have a thermocouple type J or type K, other types of thermocouples. And that's why it's important to make sure you set the right type. Because you're looking it up in a different table for different types of metals. And if you don't have the right type, you'll get the completely wrong answer. Right? So there you're typically talking about millivolts, maybe microvolts even, being developed on a thermocouple. So on the DMMs, there's also a couple important sort of settings that I want to make sure you guys are aware of that'll help you make measurements better. So on this DMM, you've got these 4 buttons around the auto here, the four arrow buttons really. And when you're in a standard measurement mode, whether it be here ohms or whatever, going left and right changes your measurement speed. The up and down arrows set your ranging, right? So, and typically you're gonna use auto range. That's makes most of your measurements right. But occasionally you might say, hey, that number looks a little odd. Let's go up a range and see what it looks like, right? So, here we're on the 100 ohm range, but we can go down to go up to a higher range, and it moves the decimal place over. So, especially in resistance, that can be useful because typically as you change ranges, you're changing the current that's being produced to then develop the voltage, right? And so, especially if you had a nonlinear device on there, it wasn't a true resistor, you could see dramatic changes based on how much current you're putting through it. And then lastly, I wanted to talk about introduce the concept of NPLCs. So really in any measurement, but it's most common in multimeters, NPLC stands for number of power line cycles. Right? So I kind of can imagine, right, this because we're drawing power from the lab, and we've got there's power supplies, switching power supplies, and a lot of these instruments, right? So if you make measurements really quickly, but pretty accurately, you could see in essence the 60 hertz moving around below us, right? It's invading our measurements a little bit. You would see noise generated at 60 hertz that's just coming from the power line. So what a DMM does that's special is it can do integration over power lines cycles. So when you set the instrument to 1 NPLC, what that tells it to do is, in essence, take measurements on the A to D over that 1/60th of a second, 16.67 milliseconds, and then average them out to get rid of the noise that's moving with the power line. So that's one good way to get rid of 60 hertz noise that's fairly common in low-level measurements. And then the last thing that's I think useful to know about the DMM is the REL measurement. So if you're looking at changes in your circuit, we can use REL to do that a lot. So here if we have our 100 ohm measurement here, and we can go ahead and REL it out, and that just makes it 0. So then changes from there you can see. So if you added another resistor, you can see what the difference is. If you added more voltage, you can see what the difference is, rather than having to do that math yourself. So that's a handy measurement there. All right, so now as we move more towards oscilloscopes, it gets a little more complicated, right? So I think pretty easy to understand when we talked about resistance and power in a DC sense, right? We could see that if the voltage stays at 1 volt continuously, the current stayed at 1 amp continuously, that would be 1 watt all the time, right? But how does that look when you're talking about really common sort of sinusoidal signals, right? And this is where the concept of sort of RMS voltage becomes important. So you might hear whenever you're talking about AC signals, it's very common for people to use the volts RMS or RMS notation. And what that really means is that the RMS is the equivalent voltage level that if it were DC would create the same amount of power as that AC signal, right? So that is, it's a great notation for calculating power, as well as sort of normalizing those AC signals, right? Because from your AC power, depending on the offset and the amplitude, you can create there's a lot of different power that is actually developed based on that and then the current. But the volts RMS allows you the notation that tells you, hey, that's the equivalent DC value. Let's keep moving. All right, so we've got our 2 volt peak-to-peak signal at about 1 kilohertz. Oops. So so presumably if you did that right, you're seeing 2 volts peak-to-peak on the scope, right? What's the RMS voltage you're seeing?
700 millivolts.
700 millivolts. Excellent. RMS. So how that's calculated is the peak voltage over the square root of 2. So not the peak to peak, which is 2 volts, but in this case, when you have 0 offset, the peak voltage is 1 volt. So 1 volt peak divided by square root of 2 equals 707 or so millivolts RMS. So, so this is exactly what the scope's doing, this measurement, right? Now, if you get the DMM across it, what does the DMM read in volts? Anybody get to that? That's all right. So when you get there, you'll find that the DMM measures the same thing, 700 millivolts, because the DMM in AC volts is always measuring RMS. That's the way AC, for the same reasons we talked about, that's the way AC volts are usually calculated. So the only time you'll really be talking about peak-to-peak values is really when you're visualizing it on a scope. Almost everybody else cares about RMS. All right. And then I think we had at least one person who was set up nicely to measure the AC or the current RMS as well, right? So if you put the ammeter here like we had before and put it into AC current mode, you'll get the current in RMS. And again, the purpose there is, hey, we want to know how much power this resistor is taking, right? We can take the voltage RMS times the current RMS and get power, get watts. And that's difficult to do really any other way with the sine waves, with the AC voltage. So that's the purpose of the RMS, and that's what we're calculating there. Cool. Questions about that? No? Good. All right. So this slide is a little tricky, but we're gonna work through it. So what this slide's trying to show you is what a digital scope is doing. Right? So a digital scope has, like all these, has really a couple key things. Its sample rate and its memory depth, and then really the time that you want to look at. Right? And there's a constant struggle here, right? Because to make the best measurements possible, especially at high speed, you need higher and higher sample rates. Right? You want to be sampling at a gigasample, or 1 e to the 9th, right? That's a billion samples a second, 1 gigasample. So that gives you the most clearest image of what's happening in high speed voltage space. But because all digital scopes have a certain amount of memory too. Ours tend to have quite a bit. But even with the sort of 12 million points of memory that's sort of standard in these instruments here, see if you're sampling at a gigasample with 12 million points, how long is that in time? Well, 12 million times 1/1000th of a second is 12 milliseconds. So you can look at 12 milliseconds in time with a super high quality picture, sampling 1 billion times a second, get all that data and convert it all and get it onto the display. If you're looking at something slower, if you want to see something that happens over a longer period of time, right? So if you want to record a slower moving signal that takes 1,000 seconds, well then your sample rate has to come down to allow that memory to fill over a longer period of time. So that's one of the challenges you'll find with a scope is you want to make sure you understand that when you set the time, because that's usually how we think about it. We turn the knob and we say, all right, I want to look at 10 milliseconds or 2 seconds or whatever. We got to be aware that the sample rate is adjusting in the background to fill that memory. Right? So on the top, sort of top middle of your screen, I think it's in the same place as this guy, sort of top middle of the screen, it shows you both the memory depth and the sample rate, really at all times. Probably says something like a gigasample or 500 kilosamples right now. So that's an important thing to remember, especially as you move towards higher speed signals. There are a bunch of settings on a scope that are relevant that we'll like to talk about quickly. So our vertical settings. So on these scopes you have a control where you select the channel. Easiest to do here. You select the channel and then the menu and the controls work for that channel. Right? And so there in this channel settings is where we do things like set up the probes. So important, first thing I do when I turn on an instrument and hook up a probe is I make sure the attenuation setting on the probe handle matches the scope. That way I know I'm looking at the right voltage numbers. The horizontal setting is the next one over here. So that sets your time, right? So the big one makes it wider or shorter time to be looking at. And you can also push that big knob. You push that and it zooms in on the signal, right? So same as this one does. That allows you to trigger on or capture a wider signal and then zoom in on a smaller segment. So that's an important capability worth knowing about. And then also in the horizontal mode is where you would set XY mode. So you probably, or you might have a couple labs that do a little XY plotting. And looking at those kind of curves, those are interesting, and that's how you get to it, is in the horizontal menu. Your acquire settings, so the acquire button there sets your acquire modes, which we'll talk about a little bit later, as well as your memory depth, and tells you what your sample rate is. And so those are the kind of the key areas, and then, perhaps the most important is your triggering, right? So triggering is one area that you can learn a lot about how to capture the wave, right? So on a scope, whenever you start it up, the trigger should be in the center, right? So you see the orange trigger marker right down at the top middle, and that's your trigger point. And so there, what it's trying to do is trying to whatever it captures based on the trigger settings you've put in, it then posts to the display. Right? So an instrument like this can trigger on simple edges, can trigger on pulse widths, can trigger on slopes, can trigger on all kinds of pulsed events. And the more you get to know that, I think easier it is to really debug systems and find problems quickly. And then the other thing to know, we won't do too much with the digital signals today, but the other thing to know about these scopes is you've got the digital connector at the bottom, which really allows you to capture bus signals. So you can capture digital signals from a computer bus, I2C SPI buses as well, and look at those signals and the timing of those in comparison to the analog signals. So one thing we want to talk about is we talked about sort of sample rate and why that's important, but this is sort of the key to that, right? Is the risks of undersampling. So when we talk about sampling, the key sort of theorem or concept is the Nyquist theory, or the Nyquist theorem, right? So it says you need to sample at least 2 times the Mach frequency you're looking for. And we would say best practice really to have it look right is more like 5 or 10. Because what can happen is, we create a sine wave based on these samples, but if you weren't sampling properly, these samples also match much higher frequency signals that are underlying, right? So that effect of thinking you have a slower speed signal, but there's really a higher speed signal underlying it, is called aliasing, right? So that's when you don't have enough sampling, you can alias on the signal, which means, basically you get the wrong information. It's saying the signal is much slower than you think than it really is, and that's causing you trouble because it's giving you bad measurements. So the next sort of thing we're going to talk about is bandwidth. So this is another concept that I think is important, right? It's clear, I think, to everyone that, hey, 100 megahertz oscilloscope has a bandwidth of 100 megahertz. Really, whatever scope you have, it has a bandwidth. And in an ideal world, right, a 100 megahertz scope would be perfectly flat and then drop off a cliff at 100 megahertz, right? And that's not how circuits look, right? So what you get is you get, circuits have a certain amount of noise, whatever, and then they tend to fall off pretty rapidly. They may do something like that, right? So that means that, so when we talk about a 100 megahertz scope, or whatever bandwidth you talk about a scope, what the person who's telling you that is actually saying is, hey, at 100 megahertz, this scope only attenuates the signal 3 dB. And really, on the from DC to there, it should never be outside of that 3 dB band, right? So there's an error band here. Right? So, but when you're thinking about that, you realize that 3 dB, when you're measuring voltage, is about 70%. 70.7% of the signal. The other thing that happens is it really affects your rise time of your measurements as well. So rise time is something we calculate typically a 1090 rise time on a pulse or something like that. We say is about 0.35 divided by the bandwidth. Right? So that's I think a complicated thing to really internalize because it's not really stretching it out in time, right? The signal is as it is, but it's measuring it as a slower signal because what's happening is you have the bandwidth of the signal itself and the bandwidth of the scope working together to slow the system down. Okay, so the other thing, the next thing I want to chat about on the scope side is what we call waveform capture rate. So we can see that, again, we're capturing a bunch of samples, finding a trigger point, putting it onto the screen. Capturing a bunch of samples, finding a trigger point, putting it onto the screen as fast as we can, right? The scopes, like the ones on your bench, can do that 20 or 30,000 times a second. A more powerful scope like this might do it 100,000 times a second. But no matter how it's doing that, reality is there's always some dead time, right, where it's not actively sampling and it's working on processing it or moving it to the screen or doing some other work where it's not live on the signal. Or an individual pulse or a different event that's happening, a glitch. It's important to kind of remember that, hey, sometimes you can miss those because of this dead time. And so having the scope in a mode where it can measure the fastest or have the fastest waveform update rate is really important to that whole process. Right? So that's all about that dead time. So really effective use of an oscilloscope and proper visualization of your signals. It's really a combination of these effects, right? Having enough bandwidth to make the signal, having enough sampling to see the signal correctly, have enough memory to be able to look through it in time and update it quickly enough, and then how it actually displays on the screen as well. So now there's a couple things I think worth looking at in what we in essence what we talk about as acquisition modes, right? So in that acquisition menu. So let's look here at a special signal. I'm going to go into this mode. I'm going to add some noise to this. So there's a sine wave with noise on it, right? And there are really 4 acquisition modes that your scope has that affects how it looks at these, right? So certainly normal is the most common. In essence, the normal, it's picking out a random sample of each sort of sample bucket, right? Because we have 4 gigasamples per second and we're only looking at 10 nanoseconds wide, we still have hundreds of points on this display. Right? So normal picks a close one. The peak detect mode for a signal like this looks a lot like the normal, but in essence the peak detect just accentuates some outliers, so it can help you find errors that way. And then average does something interesting. So what average does is it takes successive captures and overlays them and averages them together. So at points the same distance from the trigger point, it will average together to reduce the overall system noise. Right, so this is a great functionality if you have signals that are repeating, and you want to see the underlying repeating signal and get rid of the noise that's not, that's sort of non-systemic, not repeating at that same value. Right, so you can average, many of these together, up to thousands really, to get a real clear image of what that would be if there was no asynchronous noise on there. AC versus DC coupling is it's in the channel guide. It's in the channel menu, and really this is two ways for a scope to look at a signal, right? It's with or without sort of a DC block in there, so that when you have DC coupling, you're actually looking at the true signal with a voltage offset. When you switch it over to AC coupling, what you're actually doing is getting rid of that voltage offsets. Take a look at it with DC coupling on, and see how far you can zoom in on the top of that signal. And you'll see that it's a little frustrating to get there, so you got to keep going. So you can see how close you can get, how much you can zoom in to get to the top of that signal, and then switch it to AC coupling and see what that looks like. And you should find that it's much easier to sort of zoom in on that top of that signal and get a much better view because you've removed the DC offset. So let's talk a little bit about probes, just so I think we covered some of this, but so again, the probes, just like the scope we talked about before, probes really are the same. They're not flat over bandwidth. So this is a analyzer shot over frequency, but you can see they fluctuate. They can fluctuate by a number of dB over frequency as that goes. And then you've got your probes here have what is called a 10x 1x mode switch on them. So the 1x mode, which gives you the exact right voltage that's on the output of the probe as the input, 1x attenuation. That is really limited to probably somewhere between 7 and 50 megahertz. Right? So on that setting, it's really made for low-level signals, like if you're looking at sort of millivolt level signals at slow speeds. So it will attenuate or make it really difficult to see the higher speed signals up towards 100 megahertz. So if you want to look at anything really past 10 megahertz, you probably want to switch to your 10x mode. And that gives you 10x lower voltage, but the scope setting for the attenuation can change the math so it looks right. And then let's take another look at that. We talked about it briefly before, so our sort of probe loading effect. So here we've got a 99 megohm in series with 1 megohm. We're pushing 5 volts across it. Easy for the power supply to do. And then we're measuring with the DMM right now across the smaller 1 megohm resistor. So we're measuring with the DMM here. And we're getting the right answer at about 45 to 50 millivolts. Right? This one it would be 50 optimally. But if we take the scope, if we put the scope across that, let's see. So here in 10x mode, we're seeing about the right number, about 50 millivolts. Now I switch it to 1x mode, and on the DMM and on the scope, it's dropped down to about half, right? Because that loading effect in 1x especially causes another parallel route here with about a megohm. So half the current flows through each one, and that causes both your voltage and your loading effect to alter the circuit. So just be aware of that when you're measuring high impedance sources, right? That your scope might not be the best tool for that. And then one thing that's always worth doing once in a while on a scope is to look at the probe compensation point. So all the scopes you'll see have a little probe comp port here on the front, and that's what you should always see is this sort of square wave, right? And there's a little screw mount in the probe itself to make that more square. It changes the capacitance to even it out. Okay. Let's look at a couple signal harmonics. All right, so we have a pretty typical looking square wave. And now we're going to go into the math and look at what is called the FFT. So here's a 1 kilohertz square wave. So you can see a square wave has odd harmonics, right? So the first harmonic is at 1 kilohertz. Third is at 3, 5, 7, 9. So these are the odd harmonics of the signal. A square wave or a triangle wave, these symmetrical waves don't have even harmonics. In a triangle wave, you'll see we'll look at some math in a minute, but they actually drop off faster, right? So the first harmonic, third harmonic, fifth harmonic, they go down at a more geometric, at a steeper angle as you get higher frequencies. We'll look at each one. But again, the FFT, it's a fast Fourier transform, which means it's taking that voltage data and move it into frequency space. So that's really kind of the key concepts we wanted to go over today. So we'll do a little summary here. But so we talked about DMMs first. Remember, there's a number of different settings and connections to be aware of, but it's for low frequency work, DC to a couple hundred megahertz or a couple hundred kilohertz. You've got DC volts, AC volts, resistance you want to measure. You want to adjust your speed and ranging, kind of to optimize the accuracy for what you're trying to do. And then just make sure you're kind of in the right function. And think about what that function is doing, right? Is this a short circuit I'm presenting to my circuit? Is it a high impedance measurement? What's I'm doing? And once you understand that sort of theoretical, what it's doing, then you can figure out for yourself whether it's connected correctly or not, right? Should this be in parallel or series? Well, it's a short circuit, measuring amps, so I want to be in the circuit, for instance. Then on the scope side, right, we talked about a lot of things that can get in your way, right? Settings on the coupling, the bandwidth, sampling, probe loading, all sorts of issues that can get in your way, can cause you trouble if you're not used to making measurements, or if the person who was in the lab before you got the instrument in a different state than you're used to, right? So one thing that's always good to remember on these scopes, if you go into the storage menu, the bottom menu item when you hit storage is called default. If you hit that button, it'll reset it to normal settings. So a great way to get back to stage 0 if you think one of the settings might have got messed up and it's doing something a little funny. So we've got we talked about some advanced features, some math, some FFT. We use the measurements on the right side there to really look at the nature of these signals, compare those results with the DMM and see how that all works together. Hopefully that was good for you guys today. Maybe learned a couple things. We do have a lot of educational resources online. So if you have some free time and you want to spend some time on the YouTube, we've got a nice website. Our Basics Scope site has about 40 videos of how to do the things I did and some other things with the scope that you guys have. And then of course we have an IoT page as well. It has a lot of application notes and videos on some more advanced sort of debugging tools and techniques. Well, thanks so much. Appreciate it. Thank you.